Welcome to Lecture 38, 10.3 Hypothesis Testing for a Population Mean this time. So last section we did population proportion, and now we're looking at population mean. So for testing the hypothesis about a mean, if you recall in section 9.2, we learned about William Gossett, who solved the problem of how to find a distribution without knowing the population mean mu. And what did he determine? Well, he determined that t equals x bar minus mu divided by s, which is divided by the square root of n, our sample size, n, s, our sample standard deviation, mu, our population mean, and x bar. This follows a student's t distribution with n minus 1 degrees of freedom. Now we're going to use this distribution to perform a hypothesis test on a mean. Alright, so testing a hypothesis about a mean is very similar to testing a hypothesis about a population proportion, which we just did in section 10.2. So what is the difference? Well, the main difference is that we use the student's t distribution rather than using the normal distribution. And remember, so for the student's t distribution, we're not using table 5 anymore, we're using table 6, which is in the back of your book, or if you're just using the online book, that should be under Tools for Success. They have the tables under there as a PDF as well. So testing hypothesis regarding a population mean. Okay, first off, we just need to make sure that the following criteria is in place before we can test our hypothesis. Just like how we make sure something is approximately normally distributed before we can use a certain form, either z, or if it's not approximately distributed, we can't use z anymore, so then we have to use just the binomial probability. So here's the 3 things we need to check. First, the sample is obtained using simple random sampling from a random experiment. Okay, so either from simple random sampling or from a randomized experiment. That should be randomized. And then, the sample has no outliers. And the population for which the sample drawn is normally distributed. Or, so either it's normally distributed, or the sample size n is large. And what does it mean that it's large? Well, n needs to be greater than or equal to 30. Okay, that's a good one to keep in mind. The size of the sample. That often plays a part in what we can do in terms of trying to find our population or trying to find our percentage. Okay, a lot of times it's based on the sample size. And then, well, the sample values are independent of each other. Okay, so note, once again, we have 2 different methods for testing our hypotheses. Well, we're either going to use the classical approach or the p-value approach. Also note, the first 2 steps for both of them are the same for each approach. So basically the first 2 steps you're always going to follow, regardless if you're taking the classical or p-value approach. But then after step 3, that's when things deviate. So let's take a look at the classical approach and what this entails. The first thing we're going to do is we're going to determine the null and alternative hypothesis. So once again, we have the 2-tailed, left-tailed, and right-tailed. And I think that you know how to write the hypothesis, so try to write them down by yourself and check back in with me in a second. Well, once again, so h naught. We're using mu because we're thinking about the mean here. So mu 0 or h1 not equal to mu 0. H naught for left hand, so this is talking about less than. H naught is always going to be equal to. And then h1, mu is less than mu 0. And then once again, for the right-tailed h naught, we have mu equal to mu 0. That's our null hypothesis. And lastly, our alternative is it's greater than the value. Second step, we're going to state the level of significance, alpha, depending on the seriousness of making a type 1 error. Oftentimes, the level of significance is given to you. More than likely, it will be given to you on the exam. So this is where the two different approaches deviate. Okay, so for step 3, for the classical approach, what are we going to do? We're going to compute the test statistic. Well, technically for both of them, you compute the test statistic, but how you use it is what differs. And for t sub 0, that's going to be x bar minus mu sub 0 over s divided by the square root of n. And what does this do? Well, this is going to follow the student's t-distribution with n minus 1 degrees of freedom. And we're going to use table 6 to determine the critical value. Okay, so table 6, remember, is for the t-test, or the t-distribution, excuse me. So let's see, if we're looking at two-tailed, left-tailed, and right-tailed, what would they look like? Well, let's go ahead and draw basic little slope there. Oops, and let me just copy that one more time. There we go. Okay, so we have the three, excuse me. Now what are we looking at? Well, for two-tailed, we're looking at two sides, right? Looking at this area here. For one-tailed, or left-tailed, excuse me, we're looking at that side. And then for right-tailed, we're looking above. Actually, let me change that color. There we go. And what are we doing with the critical value? Well, the critical value will have negative t alpha over 2 and t of alpha over 2. Those would be the value points right there and there, which will give you the critical regions that are shaded. For left-tailed, we have negative t alpha, and right-tailed, we have t alpha for those critical areas. Next, for the classical approach, we're going to compare the critical value to the test statistic. Okay, so once again, remember what you do is you find this value, then you're going to look on the table and find it over here on the tables. And then you're going to compare the two. You're going to compare t sub 0 with the critical value that you just found looking at your table. Once you've done that, comparing them, you need to determine what you find. So we have three options, again, because we have three different versions. So if your critical value, if your test statistic is less than your critical value, t alpha over 2, or your test statistic is greater than your t value, we're going to reject the null hypothesis. So basically, what is that looking like visually? Well, that's saying that the critical value we found, the test statistic that we found was somewhere smaller than or greater than. Okay, so because it was on either end, so far away of probability, then we would reject the null hypothesis. Now, if we're looking at the left-tailed, we have if our t sub 0, so if our test statistic is less than the critical value that we found, which means it's somewhere in here, then we're going to reject the null hypothesis. Now, if we're looking at the right-tailed, if we have that our test statistic is greater than our critical value, so somewhere in here, then this time we will reject the null. And lastly, we'll state the conclusion. Pretty similar to before. So the p-value approach. We're going to determine, once again, the null and alternative hypothesis. Okay, so remember, the first two steps for the p-value in classical are the same. So go ahead and write down the different null and alternative hypotheses that we have. Hopefully you have them memorized by this point. Alright, so h naught, that's going to be mu, is equal to, and in fact that will be the same the whole way along. So let me just go ahead and copy that and paste it to both, because it is the same. And then it's the alternatives that change. So for two-tailed, we have that it's not equal to For left-tailed, we have that it's less than, and for right-tailed, we have that it's greater than. Step 2, once again, select a level of significance alpha depending on the seriousness of making a type 1 error, usually given to you. And 3, well, unless you're the person who's researching. If you're actually the person researching, that's when you decide how much of a wiggle space you want to give yourself for that type 1 error. But for the class, more than likely, you'll be given the level of significance. So step 3 for the p-value approach. You're going to compute the test statistic. In this case, they are kind of similar here, but it's what you do with it that differs from the classical approach. And this is going to follow the student's t-distribution with n minus 1 degrees of freedom, and we're once again going to use table 6 to find the p-value. Alright, and then, so let's take a look at what these look like graphically in terms of our comparing the critical and the p-value. Let me go ahead and copy this not great so looking curve. And kind of got cut off a little bit, but it looks okay. Alright, so very similar. For our two tails, as usual, we're looking at two different areas. Right and left, this should actually be equal. I didn't draw that quite as well. Left tail, we're looking at left side of a value. Right tail, we're going to be looking at the right side of a value. And what are the values that we're looking at? Well, we'd be looking at the absolute value of t0 for both of these. And the p-value that we'd be looking at is going to equal 2 times the probability of t being greater than t0. Left-tailed, what are we looking at? Well, we are looking at, once again, that t-value that we find on the table, and our p-value is going to equal the probability of t being less than t0. Right-tailed, we're looking for the p-value, this time, our t sub 0 value, of p being greater than our t sub 0 value. So remember, we're looking at the area to the right. And then, if we find that the p-value is less than alpha, okay, so alpha being our level of significance, then we reject the null hypothesis. And lastly, we will state the conclusion. Okay, so those are the two different types of ways of approaching the problem. We have the classical approach and the p-value approach. So where do they mainly differ? Well, for the classical approach, what you do is you're comparing the critical value that you find with the test statistic. What you're doing for the p-value approach is you're comparing your p-value to your alpha. Okay, so the level of significance. Mainly that's the difference. Now let's take a look at some examples. So, for example 1, we're going to test the hypothesis about a population mean using the classical approach. Alright, so we're given a simple random sample of n equals 200 to test h0 of mu equals 22 and h1, our alternative, of mu greater than 22. So first we're going to verify that the requirements to perform the test are satisfied. So once again, what were the requirements? Well, 1, it needs to be a simple random sample. And yep, we're told that it is a simple random sample, so we're good. Second, what do we need to check? So for the second thing to check is we can either look for no outliers and the population is normally distributed, or we can see if the sample size n is large, or n is greater than or equal to 30. So, since we have n is 200, so n is 200, which is indeed is greater than or equal to 30, that passes that one. And lastly, we're going to see if they're independent of each other. So for this problem, we're going to say that they are independent. We're going to assume independence. If it was a word problem, it would tell you the population size possibly. So you could either say, yes, it's small enough that we can assume they're independent. And if it does not state if it's independent or not, you can go ahead and write assume independence. And unless there was some obvious detail that maybe you should have checked on the exam, if you write assume independence, you can go ahead and keep solving with that. Which means I knew that you checked for all three, you knew what all three were, and that is good. All right, so B, let's see. Draw a distribution to indicate the area that represents the critical region. Okay, one thing I forgot to put in, so hopefully I have fixed your notes by the time you get to them. So draw a distribution to indicate the area represents the critical region, and this is with, let me change the size of my pen real quick. So with our sample mean of 22.6 and sample standard deviation of, let's see, 3.9. Okay, so let's go ahead. We're going to draw the area for the critical region. So we have our mean of 22, and we're looking at 22.6. So we want it to be greater than. That's what we're looking at. All right. So now let's go ahead and test this using the critical value approach. Or sorry, classical approach. So let's find the test statistic. And we have t sub 0 is going to be x bar over u sub 0 over s divided by the square root of n, our population. Once again, always write out the formula and then plug in the values, and then you can use your calculator to figure out the rest. So what is our x bar value? Well, we were given x bar of 22.6, and then our mean was 22 that we're testing with, u sub naught. Our sample size was 200, and our n, that I filled in the wrong one, sample size was 200, and our standard deviation was, 3.9. All right. I'll go ahead and plug this into my calculator and see what I get. All right, so I got, it is about 2.17. We can round that up to 2.18. All right, so this is our test statistic. So what do we do with it in the classical approach? Where we're going to look at the student's t-distribution with n minus 1 degrees of freedom. So look at table 6 with, and we're looking for n minus 1, so n minus 1 is going to end up being, 200 minus 1, which equals 199. Now actually, if you take a look at your, and I'm going to take a look at mine right now, at our table 6 value, sorry, table 7, I don't know why I'm saying table 6, looking at our table 7 value, 199 is actually not listed. So since 199 is not listed, we're going to go for the one closest to 199, which is 100. So look for degree of freedom closest to 199, which is 100. And then we're going to look for our alpha, in our case, which is equal to, let's take a look what alpha was. Alpha was, there we go, 0.05. So look at 0.05. So if we look at our table, underneath 0.05 at 100, we end up with 1.660. So we have that our t of 0.05, remember that's our alpha, t alpha, is going to end up equaling 0. Oops, and I accidentally put it away. Let me find it again. 100, 0.05, 1.660. All right, so what are we doing with this? Well, once again, let's take a look. Let's draw an image, this time using our test values. So we were looking at a right-tailed, right? Yep, we want it to be greater than. So looking at a right-tailed, and we had that our t sub 0 value is 2.18. And then that we have our test value, t of 0.05, is 1.660. So notice, our test statistic is inside the area, which means it's greater than. So since it's inside this area, or it's greater than, so since our t sub 0 is greater than t of 0.05, what do? We reject the null hypothesis. Period. Okay, so once again, with the classical and p-value approach, they're both going to be using table 7. But how you use it differs. Okay? So let's take a look at this time using the p-value approach. Alright, so we're told if we obtain a simple random sample of n equals 400 to test h0 of mu equal to 45 versus h1 of mu not equal to 45, we're given if x bar, so our sample mean, is 48.3 and s, our sample standard deviation, is 8.5, compute the test statistic. Alright, so we're not told to check it this time, so we're not going to go ahead and check it. So let's see, the test statistic, T0, that's going to equal x bar minus our mu naught divided by s divided by square root of n. As usual, write down the equation, fill in the items. Let's see, our x bar is 48.3. Our m is 45, sorry, our mu is 45. S is 8.5. And our sample size is 40. Okay, I'll go ahead and plug this into my calculator and see what I come out with. And my test statistic is 2.45. Alright, so we found the test statistic. Now what are we going to do? Well, let's draw a t-distribution and shade the area that represents the p-value, and then approximate and interpret the p-value. Okay, so let's go ahead and draw the area we're looking for here. Well, t sub 0, our test value, and once again, is this left-tailed or right-tailed? Ooh, this is two-tailed. So, let me erase a teeny bit of that. There we go. So we're looking for two-tailed. And on the two-tailed, so we have our t0 is going to equal, so we have the 2.45, but then we're also looking for the negative 2.45 since it's two-tailed. Okay, and then that is the area that we're kind of looking at. Now I'm going to go ahead and bring in the chart from the table. Alright, so now I have our table for our t-distribution, and we're going to use this to find the p-value. Okay, so our p-value. Well, we're looking for 2.45, right? So now this is how it differs from the classical value. For the classical one, what we would do is we would take a look, we would find our degree of freedom, maybe if it's 10, right? And then, for the classical approach, we would go along looking for our alpha and then find our value. And compare that to our test statistic. For the p-value, this is different. For the p-value, we would find the value inside our table and then take a look up at the top values. Alright, so what we first need to do is to figure out the degrees of freedom that we're working with. So the degrees of freedom are based off of our sample size n, and our sample size n was 40. So the degree of freedom, shorthanding, would be n minus 1, which would be 40 minus 1. So that'd be 39. So notice the chart I picked here does not actually have 39 in it. So I'm going to quickly bring in another chart so we can work with this. So let's see, so bringing in my other chart. Alright, so now we have the other chart, and what we're going to look for is, remember, we're looking for a degree of freedom to be 39, and we're also trying to find, let me go ahead and make this fit a teeny bit, it's so small. Okay, we're trying to find 2.45 on our chart. Okay, so 2.45 on the chart with a degree of freedom being 39. So let's see, 39, and we're going to try see if we can find 2.45 in this. So looking around, 2.45 is not actually on our table, because remember, we're finding this with our charts. If you wanted to find an exact p-value, you could use technology, so Minitab, Excel, or StatCrunch to find the exact value. We're just using the table to approximate it. So it's between these two, which means if I go up, it is in between these two alpha values. Alright, since it's in between those two, we would take the average, right? So let me go ahead and get some space here. Alright, so now we found those two alpha values that are going to be helping us find our p-value and my p-value. Okay, so we now know that our p-value is going to be in between 0.005 and in between 0.01. Alright, so to kind of roughly approximate what value this would then be, this would end up being, so for approximating, we'll take 0.01, add it to 0.005, divide by 2, and we'll get 0.0075. Now, that then means my p-value is going to be 2 times that value that I just found. And you might just say, wait, didn't we just divide by 2 and now we're multiplying by 2? That's going to give us the same thing. Why we divide? Well, remember, this is a two-tailed test, so we have to multiply by 2. But we won't always be multiplying by 2 because we won't always be working with a two-tailed test. All right? So, kind of, I guess, redundant in some ways. We're a two-tailed test. All right, so then when we calculate this out, we end up with 0.015. Once again, remember, you could find a more exact p-value using technology, but for the exam, we're doing it by hand, so you're going to approximate it off of the table. All right, so there we go. We have our p-value right there. Okay, let's take a look at part C. If the researcher decides to test this hypothesis at the alpha equals 0.01 level of significance, will the researcher reject the null hypothesis? Well, remember, for p-values, if p, the p-value, is less than alpha, then we reject. Well, our p-value is 0.015, so we have 0.015, and the question is that less than our alpha? And what's our alpha? 0.01. And the answer is no, it's not less than. So since it's not less than, we're not going to reject the null hypothesis. So since the p-value is not less than 0.01, we do not reject the null hypothesis. Okay, and I'll go ahead and actually exchange our p-value right there with the actual p-value of 0.015. Remember, that's actually an approximation, just using the table. If you want an actual perfect approximation, you would be looking on Minitab or Excel or your calculator. So now, before testing the hypothesis of a sample size that's smaller than 30, you would first need to verify that the population is normally distributed with no outliers. Okay, to do this, you would need to construct a normal probability plot and a box plot. Okay. Once you've verified this, then you could continue to test as you would normally. Probably not something I would require you to do on an exam, as it's a bit tedious to do by hand at least. All right, and notes. Okay, so the results are statistically significant if the difference between the observed results and the statement made in the null hypothesis is unlikely to occur due to chance alone. And I just sort of spelt occur there with like 3 C's. Let me change that. Okay, so translating this. Basically, it's saying if we found out that the chance of seeing what we saw, the probability we saw, is a super low chance, then more than likely the null hypothesis is unlikely. Just think back to that heads and tails result. The probability of your friend getting 4 tails in a row was a super low chance. So the chance that the tail or that the coin was fair was pretty unlikely. All right. So understanding the difference between statistical significance and practical significance. Always a good thing to check, because sometimes results you find in any sort of research might be an interesting result, but it really doesn't affect anyone's life in a wonderful way, or even in a significant way. So by definition, practical significance refers to the idea that while small differences between the statistic and parameter stated in the null hypothesis are statistically different. So even if we find out that they're statistically different, the difference may not be large enough to cause concern or be considered important. Okay, so let's take a look at an example of this. So in a certain city, they had found out that the mean travel time to work in their city was 27.5 minutes. After reprogramming the lights in the city, another study was conducted which found that a sample mean of 27.2 minutes and a sample standard deviation of 8.5 minutes. The study stated the null and alternative hypothesis as follows. Mu is 27.5 and H1, mu is less than 27.5 minutes. After testing the hypothesis at the alpha equals 0.05 level of significance, the researcher concluded that the mean travel time had indeed decreased. So wow, we found out the mean travel times decreased. So this result was statistically significant, right? It decreased. However, is this practically significant? What do we mean? Well, remember, the original work time was 27.5 minutes. And it went down to 27.2 minutes. Let's see, so how far down did that come in terms of minutes? Well, that's just 0.3 minutes. That's not a lot, right? What is 0.3 minutes? That's 18 seconds? I mean, is that... As your book says, if you see this example in your book, it's a little bit of a sassy response. It says, is 18 seconds really going to make anyone feel better about his or her commute to work? And, that is like a valid question. Does 18 seconds really make that much of a dent in your day? So, while this may have been a statistically significant result, in reality, it didn't really mean much to a person's daily life. Now, if it had come down to 18 minutes, then maybe that would have been something. All right. So, we would say the result does not seem practically significant. That might be a fun question on an exam. Practicality. All right, so note, large sample sizes can lead to results that are statistically significant, while the difference between the statistic and the parameter in the null hypothesis is not enough to be considered practically significant. So that's kind of what happened here. There was a statistical difference or significant statistical finding, but there was not enough of a difference or a difference, to be practically significant in a person's daily life. All right, so I wanted to go over real quick again the difference with working with the p-values and the classical values. Let me go ahead and just get myself some more blank space. This is not something you need to write in your notes, just something for you to know. All right, so let's just take a real quick recap on looking at the classical approach. So what is the basic plan for the classical approach? Well, you always find, your test statistic, but what do you do with it? Well, for the classical, you're going to compare the test statistic t sub 0, which you calculated, to the critical value we find in the t-table, which we call t alpha. And then we compare if it's greater than or less than, and so on. For the classical approach, for the p-value approach, we still use the table, but in a slightly different way. So what we're going to do is we compare the p-value of the test statistic to the chosen alpha level. But the question is, where do we get the p-value? And the p-value, let me go ahead and make that a capital P. The p-value. And remember how we kind of did that approximation between the alphas above? The p-value comes from identifying the test statistic in the table and looking at the alpha values above. Okay, so that's kind of what we did. We found the alpha values, but we found out that our test statistic was actually between the two, so we had to take the average. Alright, so that's sort of the main difference between the two. Once again, please email me if you have any questions on any of the homework.